Have you ever just watched an industrial robot arm? Picking something up, welding a car door. It looks so incredibly smooth, almost easy. But that simple, precise movement is actually a symphony of some seriously complex math and physics. So, how does a machine translate a simple command like grab that part into such flawless motion?
That right there is the big question we're going to unpack in this explainer. We're going to follow the entire journey, from a command typed into a computer all the way to a physical action. It's a process where a robot has to understand its own body, plan a route, and then literally battle the laws of physics to pull it off perfectly.
All right, so here's our game plan. First, we'll dive into the language robots use to understand where they are. Then, we'll see how they plan the perfect path to get where they're going. After that, we'll get into the physics they have to overcome, tackle some of the real-world glitches that pop up, and finally, we'll see how all this stuff applies to the robots zipping around our factories and warehouses today.
Okay, first things first, a robot's language. Before a robot can even think about moving, it needs a way to describe where it is and where it needs to go, and that is the science of kinematics.
The easiest way to think about kinematics is as the robot's own internal blueprint. It's a purely geometric map of its own body. At this stage, we're not worried about things like weight or momentum or gravity. Nope, it's just a coordinate system, a way for the robot's brain to understand how all its joints and limbs are arranged in space.
Now, kinematics really breaks down into two big problems. Forward kinematics is the easy one. If you know the angle of your shoulder, your elbow, and your wrist, you can do some math and figure out exactly where your hand is. Simple enough. But robots almost always have the opposite problem, inverse kinematics. They know where the target is, and they have to work backward to figure out the exact angle for every single joint to get there. And let me tell you, that is a much, much harder mathematical puzzle to solve.
And this just shows you how tricky inverse kinematics can get. For a classic robot arm, there often isn't just one right answer. In fact, there can be up to 8 completely different poses. Elbow up, elbow down, wrist flipped around, that all put the tool in the exact same spot. The robot's controller has to calculate every single one of those possibilities and then pick the best one, all in a tiny fraction of a second. It's incredible. Okay, so thanks to kinematics, the robot knows the starting joint angles and the ending joint angles. But it can't just, teleport. It has to actually plan the journey between those 2 points. This is where trajectory generation comes into play. If kinematics gives us the start and end coordinates, you can think of trajectory generation as the robot's own personal GPS, giving it turn-by-turn directions for the entire path. It's not just a straight line. It's a super detailed plan that lays out the exact speed and acceleration for every single moment of the trip. This is what ensures that the motion is smooth and controlled, not jerky and chaotic. So how does it work? Well, it really breaks down into these 3 key steps. First, a programmer defines the most important points along the path. Then the system uses that tricky inverse kinematics we just talked about to translate those points into the specific joint angles the robot needs. And finally, it generates a nice, smooth mathematical curve that connects all those joint angle waypoints over a set amount of time. Now that smooth curve is absolutely critical. It's usually generated using a special kind of math formula called a cubic polynomial, which makes sure the robot's speed and acceleration change gradually. Without this careful planning, the robot would just jerk violently from one point to the next. Not only is that super inefficient, but it could actually damage the robot's own motors and gears. So, we have a location and we have a plan. But a plan is just theory, right? Now the robot has to actually do it. It has to physically move its heavy metal parts through the real world, fighting against the forces of nature every step of the way. And this brings us into the world of dynamics. So, if kinematics was the geometry of motion, dynamics is the physics of motion. It answers the really important question, how much torque, or rotational force, does each motor need to pump out to actually follow the plan, especially when you consider all the physical forces that are working against it. And believe me, there are a lot of forces to fight against. You've got inertia, the basic resistance of each heavy part to starting or stopping. You've got these really complex rotational forces that pop up whenever multiple joints are moving at once. You've got the constant nagging pull of gravity on every single piece of the arm. And of course, you've got friction inside all the joints. The robot's brain has to calculate and counteract all of these all the time just to stay on its path. Now, the flip side of dynamics is something called statics. This is less about moving and more about applying force when you're standing still. Statics is what helps engineers figure out how all that motor torque translates into the actual pushing or gripping force the robot can use with its tool. At this point, it sounds like a perfect system, doesn't it? We've got a plan, we understand the physics. What could possibly go wrong? Well, the real world is never that clean. It's messy. It's full of tiny imperfections.
This quote just perfectly captures the biggest challenge in all of robotics, the gap between the perfect computer model and the messy physical reality. All the math in the world can't account for tiny misalignments in the factory or small variations in manufacturing. Let's look at a couple of the biggest practical headaches this creates.
One of the most common and kind of weird problems is called a singularity. Think about your own arm for a second. If you stretch it straight out, your elbow locks, right? You literally can't move your hand any further away from your body. Robots can get into similar poses where their joints line up in just the wrong way, and they basically lose the ability to move in a certain direction. They get mathematically stuck, and the path planning software has to be smart enough to steer the robot around these problem spots.
And then there's the whole setup process, which is kind of like tuning an instrument before a concert. Before a robot can do any useful work, it has to be mastered and calibrated. Mastering is where it syncs its digital brain with its physical body, usually by moving each joint to a known zero position. Then, tool calibration tells the robot the exact size, shape, and position of whatever tool it's holding, right down to the millimeter.
Now, all these amazing principles, kinematics, trajectory, dynamics, they were all basically perfected for those big stationary robot arms you see bolted to the factory floor. But they also form the foundation for a whole new generation of robots that actually move through our world.
So, in today's warehouses, you'll mainly find two kinds of mobile robots. You've got the older AGVs, or automated guided vehicles. Think of them like trains without tracks. They just rigidly follow a fixed path, like a magnetic stripe on the floor. But the newer, smarter kids on the block are AMRs, or autonomous mobile robots. These guys actually build a map of their surroundings and can plan their own routes, even driving around people or boxes that get in their way.
And you can really see how the technology has evolved just by looking at how these things are guided. The earliest systems used actual wires buried in the concrete floor. That eventually gave way to simpler stuff like magnetic tape or even just painted lines. The more modern systems use lasers to look for reflective beacons on the walls, or they use inertial navigation, kind of like what you'd find in an airplane.
So let's just bring it all home. That simple act of a robot picking up a cup, it's not simple at all. It requires a whole geometric language, which is kinematics. It needs a detailed map for its journey, which is trajectory generation. It needs to understand physics to apply power, which is dynamics. And it needs a constant reality check to make sure its plan matches the real world, which is calibration.
It is just an incredible fusion of software and hardware, and it really makes you wonder, now that we're getting so good at the pure mechanics of motion, what's the next great hurdle? Is it better perception, faster decision-making? As these robots move out of the factory and into our daily lives, that's the next big, exciting question we're all going to have to answer.